In search for unseen dark matter, physicists turn to shadow realm. Scientists hunting unseen dark matter are looking deeper into the shadows. With searches for a favored dark matter candidate, weakly interacting massive particles, WIMPs coming up empty, physicists are now turning to the hypothetical dark sector, an entire shadow realm of hidden particles. The concept has been percolating for 7 or 8 years, but it's really coming to the fore now, says Jonathan Feng, a theorist at the University of California, Irvine, UC. This week, physicists will meet at the University of Maryland, College Park, for a workshop, sponsored by the U.S. Department of Energy, DOE, to mull ideas for a possible $10 million dark matter experiment that could go ahead in the next few years. The effort would complement the agency's current experiments, including the flagship WIMP search, LZ, a $76 million subterranean detector under construction in Lead, South Dakota. And many researchers believe DOE should focus on the dark sector. Jim Segrist, DOE's Associate Director for High Energy Physics in Washington, D.C., says the goal is to fill in any gap in DOE's searches for dark matter, which makes up 85% of the universe's matter. Is there anything we're missing? WIMPs, dreamed up in the 1980s, once seemed the perfect candidate for dark matter, which shapes the visible universe with its gravity. WIMPs would weigh a few hundred times as much as a proton and interact only through gravity and the weak nuclear force. A simple calculation suggests just enough of them should linger from the Big Bang to account for dark matter today, a selling point known as the WIMP miracle. In addition, WIMPs emerge naturally in many versions of supersymmetry, a concept that solves key technical problems in the standard model of the known particles. However, physicists have yet to detect WIMPs bumping into atomic nuclei in underground detectors. And the world's most powerful atom smasher, the Large Hadron Collider, LHC, in Switzerland, has seen no sign of supersymmetry or WIMPs. The no-shows have led physicists to turn to the dark sector. They speculate that dark matter might consist not of a single massive particle tacked onto the standard model, but of a slew of lighter particles and forces with tenuous connections to known particles. See illustration. For example, in the familiar universe, massless photons convey the electromagnetic force. In the dark sector, a massive dark photon would convey a dark version of electromagnetism. Theorists generally expect that ordinary and dark photons would subtly intertwine or mix. Very rarely, then, a particle interaction that would normally produce a high-energy photon would instead produce a dark photon. Higgs bosons and neutrinos would connect similarly to the dark sector. Thanks to these portals, the infant universe should have produced the right amount of dark matter, much as in the WIMP miracle. Dark sector particles would be much lighter than WIMPs, less than the mass of a proton, so physicists don't need the energy of the LHC to blast them into existence. A much lower energy but intense electron beam could do the trick. When electrons crash into a solid target, they radiate abundant photons, and could occasionally generate a dark photon. The Continuous Electron Beam Accelerator Facility, CEBOF, at the Thomas Jefferson National Accelerator Facility in Newport News, Virginia, supports just such fixed-target experiments. In 2010, physicists on the A' experiment at CEBOF searched, without success, for dark photons decaying into telltale electron-positron pairs. Last year, physicists on the heavy photon search used CEBOF to try again. In future accelerator experiments, physicists might simply track the scattered electrons instead, looking for a distinctive kink in an electron's trajectory that would result when it emits a dark photon. Or, as with WIMP detectors, physicists could try to detect dark sector particles drifting in Earth's vicinity. Because WIMPs are heavy, physicists search for them by looking for the recoil of heavy atomic nuclei such as those in liquid xenon. That technique won't work for much lighter dark sector particles, which would bounce off a heavy nucleus like ping-pong balls off a bowling ball. Instead, physicists could look for the recoil of wispy electrons, perhaps in a device akin to an existing WIMP detector, says Catherine Zurek, a theorist at Lawrence Berkeley National Laboratory in California. Or they could create a frigid bath of light nuclei and superfluid helium, and look for tiny quantum vibrations triggered by the collisions. Another option would be to look for the breaking of free-flowing pairs of electrons in a superconducting metal. In part because light-dark matter particles would be more numerous than WIMPs, a detector for them could be much smaller and cheaper than a WIMP detector, Zurek says. LZ will contain 7 metric tons of liquid xenon, whereas a detector for light-dark matter particles could weigh a kilogram, she estimates. After the workshop, physicists will lay out their ideas in a white paper that DOE will consider over the coming months, although Segrist cautions the $10 million isn't guaranteed. Some hope the agency will quickly mount a shovel-ready experiment, in particular an accelerator-based effort that looks for the dark photon by the kink trajectory method. For $10 million you could build a really nice detector and set it down next to an existing accelerator, says Timothy Tate, a UC theorist. Others would prefer to develop techniques to directly detect light-dark matter, even if it takes longer to mount an experiment. I really hope this R&D can be part of the program, Zurek says. Joanne Hewitt, a theorist at SLAC National Accelerator Laboratory in Menlo Park, California, says she hopes DOE will seize the opportunity to launch not just a single experiment, but a more comprehensive 10 to 15-year program to probe the dark sector. Such experiments cover a very important range and they're cheap, she says. It really makes them must-do experiments.